Imagine a cloud of particles, all interacting and moving randomly in three-dimensional space. When an exam asks for the total electrical state of this system, it looks like a nightmare of spatial geometry, calculating distances and angles for every single interaction. But the net charge calculation collapses that geometry. The messy 3D cloud becomes a simple list of numbers: +1, +2, -3, +4, and -5. This calculation ignores vectors entirely. Using basic addition, the system sums to -1. Regardless of how scattered the pieces are, the net electrical identity of the entire system remains a single calculable value. Physics textbooks define this as the additivity of charges. It means the total charge of a system is the algebraic sum of every individual charge inside it. Charge is a scalar quantity. It possesses magnitude, a size or amount, but it has no directional component. This makes charge mathematically identical to mass. When you add apples to a bag, you sum their weights. You don't calculate the angles they're resting at. However, mass and charge behave differently. Mass only grows positively, while charge exists on both sides of zero. Because protons are positive and electrons negative, adding particles can result in opposing values canceling out, leaving a smaller net total. The scalar nature of charge turns a problem of spatial arrangement into a process of basic accounting. We track these values on a charge ledger. Positive charges act as left column deposits. Negative charges are right column withdrawals. We tally +7 against -8. These values nullify each other to reach a net balance of -1. This accounting logic stops at the charge itself. Quantities like electric force are vectors, which require trigonometry and spatial geometry to solve. Errors often occur when trying to apply vector math to a scalar source. A coulomb of charge contains no directional data and cannot point left, right, up, or down. The property of charge exists independently of the angles or trajectories it might eventually create. Electrostatics calculations resolve once the scalar identity of the charge is isolated from the vector forces it produces. Consider a solid object in front of you. Inside, hundreds of tiny localized charges are constantly vibrating and shifting positions. Despite that internal movement and the distances between those particles, the mathematical total of the system remains rigid. From a distance, those billions of scattered charges behave exactly like a single point charge containing their net sum. For any exam problem, find the total charge by using signed algebraic addition. Never assign it an orientation or a path through space. A force is defined by its trajectory. The charge that generates it remains a simple numerical sum, indifferent to its location or its place in the void.